Yeah, so welcome to all the Level 1 NCEA physicists out there. Today we're going to go through some revision. So we're looking at the 2022 NCEA Level 1 paper. So for those just joining, use the live chat if you wish to ask questions as we go through it, because I've got both my screens up. Right, so let's get cracking, and we'll basically start by presenting my screen. So share my screen. Might take a bit of time. There we go. Okay, so you should start seeing the paper there. We'll just be working through it. There we go. So NZQA Level 1 Science 2022. Okay, so let's just crack on. So the first question from 2022 was the America's Cup boat. And what it basically gave in the first question was a distance time graph for an America's Cup boat sailing across Waitemata Harbour in Auckland. And they've broken down the motion into 4 different sections, A, B, C, and D. Okay, so if we look at our graph there, I'll just make it a little bit smaller so we can see the entire graph. There we go. Okay, so it asks the question, describe the motion of the boats in the 4 sections. And basically it breaks it down: section A, section B, section C, and section D. Okay, so for section A, you will see it's slightly curving up over those 20 seconds, the motion over the 100 meters. So if you see that curving up in a distance time graph, that means that the object is going to be accelerating. My very nice doctor's writing there. Okay, it's accelerating. And for section B, from 20 seconds to 40 seconds, you can see it's a nice straight line in terms of the gradient of the distance time graph. So that's known as constant speed. Okay, so if you see that, the distance time graph, that nice straight line graph, it's constant speed. I really need to work on my writing. And for section C, now you'll notice that it's also that same kind of shape. It's going straight up in a linear fashion. So it's also constant speed. It's a higher speed because of the gradient is larger, but it's still a constant speed. And finally, for section D, it's flatline. So it basically traveled 800 meters and stays at 800 meters for the 20 seconds between 80 and 60 seconds. So that would mean it's basically stopped. Okay. So for that particular question, in order to get achieved, you would have to get 2 out of the 4 correct. And then to get merit, you would have to get all 4 correct. So that gives you an example of the level required to actually get merit in that question. So it's 1A. I'll make that a bit bigger. Okay, so part B of that question, part BI, on the axes below, it says sketch a speed time graph for your journey. Section C has nicely been done for you. So if you're going to sketch it, what we'll do is you want, that's a speed time graph. Okay, now moving from a distance time graph to a speed time graph. So be careful. Always look at the axes to see if you're working with a speed time graph or a distance time graph. And you can see that it goes up from 0 to 20 there. Okay, so that calculation basically comes from the 100 divided by 20 there. Okay, so that's your 20. In 20 seconds, it goes at a speed of going up there, constant acceleration. And then because it's a constant velocity, or constant speed, in section B in the distance time graph we've already done, okay, that means that for a speed, it's going to be for part B, also flat line as well. Okay. Now remember, I did mention it in the last question, the first question, that the gradient of section C is greater, okay, than that of section B. So they're both traveling at constant speed, but one has a greater gradient. So that actually means it just jumps up like that. So just connect it down like that. Okay. And then finally for section D, it's now back down to 0 speed because it's going to be staying in the same place from the first graph, that distance time graph. So it just goes straight down. There we go, to 0 for section D, and it just stays at 0 speed right there. Okay, so in order to get a achieved for that question, that would be getting 1 section correct. A merit would be 2 sections, and an excellence would be getting all 3 correct. Okay. So then we have calculate the speed of the boat in section B of the graph. And remember, it always says show your working. So we're trying to calculate the speed. Okay, so remember our equations are for speed. So velocity equals delta D over delta T. Remembering delta just means changing. Okay, so for section B of the graph, if we go up to section B, there it is there. So I'll do it all up there. This is the section we're looking at here, this section here. So the change in distance, it's going from change in speed. Let's go back in the first graph. Oh, tricky. Okay, so we're looking at this section here. Okay, so a change in distance only over section B, so we're only working in this part here. Okay, is going to be 300 minus 100, okay, which equals 200 meters. And then our change in time will be 40 minus 20, which equals 20 seconds. Okay, so if we plug that into our equation at the bottom, our change in distance will be 200, and our change in time will be 20, which equals a speed of 10 meters per second. Oh, make it a little bit tidier. It's not really tidy. There we go. Okay, and if you get that correct, that's your achieve point. 1 achieve point. So you can see where the marks are coming from. So then we move on to part C, which looks to be a forces question. Okay, so on the diagrams of the sailing boats below, draw and label arrows to show the size. Okay, so you want to look at the command word, draw, label, size, and direction. Okay, of the horizontal and vertical forces acting on the boats in section A and section B of the boat's journey. Okay, so basically for the forces on section A, you've got, I guess, a thrust force. Okay, so you'd label that T, thrust force, and you'd have, I guess because we're dealing with fluids, it would be a drag force in that direction. Then you'd have the weight force, which people tend to forget about. And the one they usually forget about is the the normal force or reaction force. Okay, now we know that in section A, if we go back, section A is accelerating forward. So that means that the drag force is slightly smaller than the force of thrust caused by the wind. Okay, but the weight force and the normal force balance out. And that means that you're going to get a net force in the forward direction. Okay, and for section B, okay, we'll just look at section B as well. So here we have section B, it is constant speed, so there's no acceleration. So that means basically all the forces are nicely balanced. Okay, there's the normal force, that's the work, the weight force, the thrust force, and the drag force. And because they're all balanced, Newton's second law of force, net force equals mass times acceleration. There is no acceleration, therefore there's no net force. They all cancel each other out, which is part of the conversation that you have in part D. Okay, so wait, let's go through the answers there. So in terms of getting achieved, if you correctly name two of the forces, okay, that's your achieved. Merit would be getting one of the diagrams correct completely. Okay, or two pairs are correct, and excellence obviously is all good, all correct. So again, nice, easy excellence question potentially. So in terms of part D, then it's compare and contrast. So when we have these key terms like compare and contrast, you know you're working with excellences in terms of the mark scheme. So compare and contrast the forces acting in section A with the forces acting in section B. And the things you should consider are both the horizontal and vertical forces, which you can use your diagram for, the size and direction of the forces, and the motion of the boat in both sections, and the net force in both sections. Okay, so basically, the net force determines the motion. So if you have a net force of 0, then it's going to either be at rest or at a constant speed. And if you have a net force which is either negative or positive, then you're going to have either deceleration or acceleration. Okay, so let's look at section A and section B. Okay, so for section A, the weight force equals the reaction force. And it's actually the same case for section B. Okay, so you'll get no acceleration in the y direction because of that. And in section A, the thrust force is greater than the drag force. Okay, and that's why you're getting your acceleration. Whereas in the other example, and that's in the x direction. And in the other example, the thrust force equals the drag force. So it's going to be at a constant speed. Okay, so that's constant speed for section B. Okay. And that will be where you get your excellences. Okay, so for get and achieved, you're essentially this thing here, the idea that balance forces, balance of motion is constant, or that because the thrust force is greater than the drag force, you're going to get acceleration. That will be an achieved, either or. So it's an or statement. To get merit, you have to have both. And the excellence is linking the upward and downward forces that are equal and opposite, and hence no vertical acceleration. It's not going to sink, or it's not going to go down or fly up into the air. So you basically, the whole focus of the question is about net forces. Okay, quite a bit there. And then we have question 2. Okay, so question 1 was about motion and using velocity acceleration graphs, speed time graphs, ideas around that. Velocity, essentially, of course, you may have learnt, is basically speed with direction. Right, so question 2 is about sandboarding in the Cape, or Cape Reinga, and due to copyright, there's no pictures there. Okay, so you've got a sand hill has a vertical height of 25 meters, and Ariane and her sandboard have a mass of 55. So again, you're kind of just thinking about what kind of equations will we be using. We're talking about a distance here, and we've got a mass. So this is the classic question usually used in NCEA 1, being able to explain the difference between mass and the weight, between mass and weight, basically. Okay, so that's always, I think, as a general rule, going to be asked as a question. Okay, so mass is just basically the amount of matter. Okay, that's pretty much all it is. It's just the amount of matter in Ariana and her sandboard. Okay, whereas weight is the downward force due to gravity, I think would be the best way to say that. Due to gravity. Okay, so basically, students usually get this question wrong because we use mass and weight interchangeably in non-science contexts. Essentially, mass is the amount of matter in a substance, and weight is a downward force due to gravity. So you can be weightless in space because there might not be gravity in space, but you'll need to be massless. I wish that was the case because I might need to lose a little bit of mass. Okay, right. So next question says, well, Ariana carries her sandboard to the top. So again, we're talking about distance and time as well. Calculate the work done by the climbing the hill. Okay, so what do we got? We've got from up here, we've got the idea of, so I've got a height, a distance. Okay, so 25 meters. We've got a mass of 55 kilograms. Okay, and indirectly, we also have a force because we've got a weight force, which is going to be 55 times 10, because remember, also from your equations, that weight equals mass times gravity, and gravity is usually 10 in level 1 exams. Okay, so it's going to be a weight force of 550 newtons. Okay, so that means that we go to our equations, and the equation I would choose, because we've got force and we've got distance, is force times distance. And if you plug in the numbers, our force is the weight force, and our distance is 25. That gives us, just move it down slightly, or move it up. 550 times 25, 1370. 13,750 joules. Okay. Yeah, so because joules and energy are different sides of the same coin. So work is measured in joules, or it could be possible you would be allowed Newton meters. Okay, so that's fine, because Newton meters are essentially the same thing. The units of force are newtons, of course, and distance is meters, so Newton meters, and you can also use joules. Okay, so in terms of that question, actually the first question here, that's achieved if you get definition correct for, okay, so achieved would be getting 1 definition correct, and merit would be getting 2. Okay, and for this one, basically, if you get the achievement point is getting the answer correct. but these are multi-point questions. Okay, so next one from calculate work done to climb the hill. Calculate the power that is used to climb the hill. Okay, so we've just calculated work, and power equals work divided by time. Another equation that you have to know. Okay, so do we have a time? Do we have a time? Yes, we do. 120 seconds above. Okay, there you go. 120 seconds above. So that equals work is from the previous answer 13,750 divided by 120, and watt is the unit of power. Obviously, watts are, and that's 114.6 watts. Okay, and that's where you get your merit from, being able to calculate both of those. And the last question is the excellence question, because it's always got the explain part. So the explain part's always trying to probe and have higher thinking skills. So explain how she could lower the power output required to climb the top of the hill. Okay. So in terms of doing that, to reduce the power output, so if you look, so it's basically power equals work over time. So we want to lower the power output. So the only thing you could do is increase time. Okay, so if it takes longer to climb the hill, that will reduce her power. Okay, and that is going to be your excellence point. That's like thinking. Okay, so time basically has to go up because it's an inversely proportional relationship. In order for power to go down, so you have to increase the time that Ariana takes to climb the hill. Okay, so next question says Ariana rides her sandboard to the top in the 25, so looking at distance again. Calculate the gravitational potential energy of the sandboard at the top of the hill. Okay, so again, we look at the things we've got. We have mass, we have gravity, and we have height. So the equation that you'll be using is EP equals M times G times H. Okay, so you plug in the numbers. So her mass from earlier in the question was 55. The gravitational field strength still times 10, and the height again is 25. You plug in the numbers, and you get the correct answer of, oh, look at this. It's 13,750 joules. Oh, that's kind of interesting, isn't it? Because that's exactly the same as the amount of work it takes to climb the hill. There's no coincidence in that, because basically the energy is required to do work, and you do work to create energy. Okay, so they're different sides of the same coin, hence why they have the same units of joules. And then we have speed at the bottom of the hill is 12 meters per second. Calculate the kinetic energy of Ariana and her sandboard at the bottom of the hill. So again, it's the importance of remembering these equations. So kinetic energy equals half mv squared. Okay, so it's basically half times her mass, which was 55, times the velocity, 12 squared, so 144 times 55 times a half, and that will be 3960. Okay, and basically just by attempting those questions, that gives you an achieved. Okay, and if you get those two correct, there's your merit. And with all questions in NCEA, there's always the explain question, which is the extending the excellence question, showing comprehensive understanding of the physics. So then it says explain the difference between her gravitational potential energy, the EP, at the top of the hill, and the kinetic energy at the bottom of the hill. Okay. So basically, it's, as you can see from the numbers, so let's go up slightly there with numbers. 13,750 is the EP, and 3960 is the kinetic energy. So that basically is saying that not all, can I say that? Yeah, EP, not all potential energy is converted to the kinetic energy. Okay, some is lost, or what do you think is some is lost? And what do you kind of think that lost in terms of energy? Lost as either heat or sound. Okay, and that's where your excellence point comes in, because you're thinking a bit more deeply about it. So you have to get basically everything right in the question. Okay, so that's question 2. And then we have question 3. They're obsessed with steels by the looks of things. So this is a pressure question, because you get the equation for pressure. Okay, so identify which of the letters represents in the following formula, including units that are used. So I've already kind of given it away on how to, look at that equation. So capital P, this letter represents the term of pressure, and the units are pascals or Newton over meters. That's also allowable. F is force, which we've looked at in question 1 and 2 already, and the units are the Newton. And A is area, and remember, it's always in meters squared. Okay, so if you get 2 units and 2 representational definitions correct, that's achieved, and if it's all correct, then that's merit. Okay, so really do need to know your formulas. Okay, and then we have cars need effective brakes to drive down a hill. A brake system in a car uses 2 pistons, a small piston and a small area with a small area. Okay, so you've got small piston, small area, large piston, large area. Okay. And braking causes a small piston to move with force. So we're looking about forces here. So force 20 newtons and an area. So we've got, look at Newton. We've got force and area. So we can calculate potentially the pressure. Because remember, we've got our equation from just above. Pressure equals force divided by area. Okay, so basically it's a show question. So it's pushing in the numbers. So the pressure basically is 20, so the force, okay, from the question is 20, and the area is 0.008, and that's going to be, if you do the calculation, 2,500 pascals, which is exactly what you're told is the correct answer. Okay. And then the pressure is the same in all parts of the braking system. The large piston has a larger area of 0.04. Okay, so it's got a larger area. Calculate the force with a large piston when braking occurs. So again, we're just using our equation. Pressure equals force divided by area. So the so we then so we want to know the force, so we have to rearrange the equation. So it's important we can do that. So pressure times area. We then plug in the numbers. Our pressure was 2,500 from the previous question. And now our new area is 0.04 from the new question. And that gives us an answer of 100 newtons. Okay, so if you get one of the questions right of I and II, then you get an achieved. 2 is you've basically got the correct answers or you make a mistake in your rearrangement. That's your merit. And 3, you get everything right. There's your excellence. Okay, so pretty straightforward, really. And then we have a car is moving along a flat road at a speed of 20 meters per second. Okay, so we've got a speed of 20. This comes to a stop 4 seconds. Calculate the acceleration of the car over the 4 seconds. Okay, so it's going back to motion questions again. So acceleration equals change in velocity over change in time. We're told the change in velocity is going to be, well, so when it comes to the stop, that means it's going to be 0 meters per second. Okay, it's stopping. So it'll be 20 minus, oh, actually, no, it's not. because it's a little trick, it ends. Okay, so change in velocity equals the velocity final minus the velocity initial. That equals final velocity is 0 minus 20, so minus 20 meters per second. And our change in time is from the question. There it is, 4 seconds. So 20 minus 20 divided by 4 equals minus 5 meters per second per second. So be careful with the units, of course, because now we're talking about acceleration, not velocity. And then we have a car and driver have a mass of 1,000 kilograms together. So I've got a mass now. Okay, so mass. Calculate the force. Okay, so dealing with the force required to stop the car. Okay, so force equals mass times acceleration, which we looked at briefly when we looked at the scaling example in question 1. So our mass is 1,000. Our acceleration is minus 5 meters per second to the minus 2. So it's going to be 5,000 newtons. Now, why isn't it negative? Because it's the force required to stop the car. It's going to be equal and opposite, which is Newton's third law. So to stop the force of the car, which is negative 5,000 newtons, you need a force of positive 5,000 newtons to make that happen. Okay, so in order for the achieved merit excellence part, I'll explain the direction of the force. And that, okay, that kind of gave away that. Okay, so basically the force, as I just said, is in the opposite direction, okay, of the car. Okay, which is basically, can't care. Which is basically Newton's third law there. Equal and every action force has an equal and opposite reaction force. Okay, so if you mention it's an opposite direction and you attempt the first calculations, that's an achieved. If you get the two correct two correct calculations and you mention the direction, that's merit. And the excellence part is the force is in opposite direction of the car as car slowing down, if I mention that. And that's your excellence. So decelerating is one negative. Okay, and that will be your excellence point. Okay, so that's that question there. And that, ladies and gentlemen, is the complete paper. So yeah, so if anybody is watching, be sure to put it in the chat and I'll stop sharing. And if there's any questions, I am here to help. And if not, we'll call it a day. And for those who are watching the recording, yeah, I hope you found it helpful. Okay, great. So there doesn't seem to be anybody in the chat with any questions. So all the best for next week with the level 1 external. If there's no further questions, I'll call it a day if you're not going to use the chat. So yeah, thanks for joining for those who did join, and keep your eye out on my Instagram when I'm running the heat external for the physics component. Otherwise, all the best for your exam.